Let's get started then, okay? So now we're going to talk about grates, pavement drainage grates. So we figured out what the flow is in the gutter. Now we have to get the flow out of the gutter and through the grate into whatever your stormwater is. So in this lesson, we're going to name hydraulically efficient or bicycle safe grates. You might not need that for your jobs because you're probably mostly on highways. List the variables that can affect the grate efficiency. We're going to define what frontal flow and side flow interception are, and then calculate the hydraulic capacity of the grate. So there are about 4 different types of grates. We're not going to be talking about slotted inlets. I'll mention curb opening inlets and passive, but we'll start with the grate inlets. And generally, they work pretty well over a range of slopes. They lose efficiency as the slope gets steeper because the velocities are getting faster, and it just kind of goes over the grate. One of the problems with grate inlets is that they can clog from debris, but one of the pros is that they work pretty well when they're not clogged. Curb opening inlets are usually used on flatter slopes up to about 3%, and they're really good where you have a lot of debris. If you try and put them on a slope, even 3% I think is a little bit high. If you go higher than that, then the water just flies on by. It can't make that turn because the velocity is so fast, it can't make the turn into the curb opening. So you want to think about using those on flatter slopes. Slotted inlets, they're usually very long, and they're used to pick up sheet flow. So any sheet flow you don't want to get into the road. So say it's in a parking lot or something like that, and you're seeing sheet flow coming down, you'll see it a lot of times there and pick it up with a slotted drain. And then combination inlets are pretty common. It's usually a grate with a curved opening. So here are some examples of grate and curb openings. Here's your grate. It's just the grate itself. And this is a curb opening inlet. Here's your curb opening. And you'll notice that the area in front of it is depressed. And that helps the water come down and go into the curb opening. I hope you're not laughing.
No, I'm sorry. It was a really bad pun. You said it was depressed, and I went, oh.
Yeah.
I'm sorry.
Sorry. Here's a combination of a grate with a curb opening, and again, it's in a depressed section. And this is what a slotted inlet looks like. So this is just, you have the hole up top is very long, and then there's almost like a tubular section below it, carrying the water away. So here's an example of a grate inlet. I'm not quite sure what to say about that. There it is.
It's great.
Yeah. Water comes this way, and in this particular one, the grate openings are parallel with the flow. So here's a grate inlet with the bars are perpendicular to the flow. And what do you notice about this? It's not very effective. Not too effective.
Yeah, just less velocity problem.
Yeah, and notice all this debris is at the upstream side of the grate. So is that going to add to your efficiency? No. It's blocking it off, and you have a lot of splash over. So it's not a great way to put your grate in. Here's a parallel grate, and where's the debris on this one? The downstream side, so that's a lot better, and you're seeing most of the flow is just flying in there, right? Do you see any problems with this grate?
All the litter.
Yeah, bicycles.
Why is the debris downstream?
It's that velocity. So the water has dropped in, and the velocity, that momentum is sending it downstream. So if you don't know what to do, two grates. And what you notice here is that the parallel bar grates is picking up most of the water, I think this might be coming from over here. And the perpendicular one has all that debris in it. You got a lot of splash over here, so it's not very efficient. But they just didn't know what to use. So here you go with some of these older grates that were killing cycles, basically. Not a good idea. Can you imagine coming down the road and getting into that?
You know, we should have at least gotten her bike out before taking pictures.
So here's, this was a developer who put this in, knew that the grate wasn't bicycle safe, so they're warning people. So they put the reflectors in here, they put reflective paint on here. Yeah, that's not good. Yeah, it's terrible. The right grade, right? But you notice too, this is a combination grate. Here's a curve opening. So, yeah, if it had been bicycle safe, it might have been a little better. So in 1977, FHWA contracted with the Bureau of Reclamation in Denver to do a bicycle safe grate inlet study. And that study came out in 1978. Kind of hard to read that, but all of our grate analyses, or a lot of them, most of them, were based on this study from 78. So here's a grate that you'll see quite a bit. It's called the P50 times 100. And it's called P50 because they rounded up millimeters. They rounded up, the spacing here is about 48 millimeters. And it's a bicycle safe grate because it has these vertical bars. So it's used quite a bit. And the good thing is it's pretty much efficient. It does a good job. Now, a lot of times you'll see the P50 grate, not the P50 times 100. The 100 is because these are 10 millimeters approximately apart. So it's about 100 millimeters. You'll see them without these bars, and that's called the P50. And that one is not bicycle safe because the tires can go right through here. So be aware. We're going to see a cross section of these. This is the P50. So this is the plan view here. I know that yellow is a little hard to take. And then the bearings underneath. This is the side view cross section. And then the P50-100 now has the bars crossing it, and they're at the top. So that keeps your bicycle tires out of there. This one is a narrow bar grate. The bars, these bars are even closer, and they thought they were bicycle safe, but tires, bike tires, road tires, have gotten a lot narrower, and there are reports of cyclists going in these things, so be careful. I'm a cyclist, so watch your designs. Then we have curved vein grates. And this is what it looks like from the top, and the flow's coming this way. And it kind of helps the water make that turn into the grate. And they're very efficient, so it's nice to have. This is a curved vein grate, but what's wrong with this picture?
It doesn't have the crossbars.
Doesn't have the crossbars, exactly, so it's not pedestrian safe. You walk on that and sure, if you
Get those flip-flops.
you might not get your foot out. So here we have a 45 tilt bar grate. It's similar to the curved vein, but it's just curved on this side. It's not going like this. That's a 45 degree. Does the same thing. It helps the water go into the grate. Pretty efficient. And then we have the 30 degree, same thing, curved vein, tilt bar grate. So. And here's a tilt bar grate. Do you think this is good?
It's still kind of big.
Really big. It's
Yeah.
not pedestrian safe. Can you imagine? I feel like I could lose my whole leg in there. So yeah, that's not a good one. And really the thing is, you want these bars to be closer spaced and you want them on top, not down into the curve. So this one is a safe grate for pedestrians. Then we have the reticulate grate. It's kind of, or it can be called a honeycomb. They're not that wonderful. You have any ideas why?
They're not strong enough.
Not strong enough?
Looks like they collect debris a lot.
Collect debris, yeah. They can collect a lot of debris, and because this is almost, it's not really perpendicular, but it's getting there, they're not that efficient. So there's one in operation, and you'll notice that we have a lot of debris down here.
Which one's the flow then? Which one's the flow in that?
It's coming this way, top to bottom.
So it kind of pushes it to the far end?
Yeah, well, it pushes, oops, sorry. Hit the wrong button. So the water's coming this way and the debris gets pushed down here, but if there's splash over water, it's not going into this curve opening, it's getting thrown this way. So that's not a good idea either. I think, hang on a second. I believe this is where I want to show you something. Well, I'm going to show it to you now anyway. I don't know where I'm supposed to show it to you. So, I got a little bit. So it's showing you the efficiency of these grates. I think that's good. So this is the bicycle seat. That was a pretty good job. Not much difference. Notice that side flow too.
It looked like it.
In case you didn't get it.
What's that excess water over there in
It's probably the side flow, for the most part, it's the side flow, except on the diagonal bar, it's slashed over. You can see on the left that there's flow coming this. So we have seen these predictions correctly. Yeah. A lot of these grates, they'll actually say curve and have an arrow facing this way. The other way. They're installed.
Have they
think I know what you're saying. I think it's just that.
Probably be easier to keep up.
Yeah, exactly. Sometimes maintenance folks and I've seen curved grates. So in one of our classes, we're going to have a team that actually show you some improvement. Is that honeycomb? Not working so great. So you can see what we're talking about then. I thought that was interesting. Was it worth watching? Okay, so when we're talking about interception of a grate inlet, we're talking about the frontal flow, and that is the flow in front of the grate that's coming towards it. And then you have the side flow. Okay? Where do you think most, or where can you see from this, where do you think the most flow is? In the frontal flow, in the gutter. So to figure out what our intercepted flow is, we can use this equation, which says the intercepted flow is equal to the inlet efficiency times our design flow. It looks pretty easy, but then we get an equation for the inlet efficiency. Yeah. So the efficiency is equal to the percent of total frontal flow intercepted plus the percent of side flow intercepted times 1 minus the frontal to total flow ratio, at least of 0. Okay. So you're thinking, well, how do I find RF and RS? Here's how you do it. The only problem is we don't know that V sub 0, the splashover velocity, and you have one equation, 2 unknowns. What are you going to do? So what we can do is go to this. So we can go to this chart. And in this chart, you start with your length of your grate. You go up to what kind of grade you have, and then you can find your splashover velocity, but more importantly, you can come over to the velocity in the gutter, and then come on down and find out what your RCF is. So you can do that. In this case, it's a reticulum grate, and our splashover velocity is about 0.58, somewhere in there. You can come over to your 8 feet per second, which is what they're telling us we have here, and come down and your R sub F is about 0.81. So that's a lot better than that equation. Okay, and then for the side slope interception, we have this equation. Do you think we have a chart for this too? You hope so, yeah. So unfortunately, I had to take a picture of this, so I couldn't get rid of this. Is just metric. We use 0.15 in English. So for this one, we go to this chart, and I think we start with the cross slope. Yeah, and in this case, it's 0.25, and our length of grate is 2 feet. We go up to the velocity, which in this case was 4 feet. And we come across and we see that our side slope interception is 0.06. It's probably about 0.063 or something like that, or 6.3% of side slope interception for the grate. Any questions about that? Yeah.
That's only valid if your spread is within your roadway, technically. If all your flow is frontal flow, then you wouldn't even have a side flow, so that
That
your
is
side
correct.
flow is 0.
That's correct. So if,
Say that again.
so if you don't have, if your gutter width is big enough that the capacity of the gutter is intercepted by the frontal flow, the grate, so all the gutter flow is coming down and it's the same width as the width of your grate, so gutter flow and frontal flow is equal, it's all going to go into your grate, theoretically. So you would have no side flow.
So you would want to know your depth and your spread before you started calculating your flow.
Yeah, good point. So here's a great inlet interception. How much flow do you think this is collecting? How about the frontal flow? Yeah, it's probably collecting most, if not all, of the frontal flow, and it's collecting, it looks like down here, just a tiny bit of the side flow. Okay. So I want you to look at this. We don't use it for design or anything, but it's just an interesting graphic to use. Just look at it for a few minutes, and then we'll talk about it. So what do you think about what goes on with these grades up to about 3% on longitudinal slope, somewhere in there? Can you make any observations?
It's not dependent on the grade shape.
Right. They almost all work the same up to about 3%, right? And then as the slope increases, the first one to fall off to not be so efficient as this reticulum grate, and then it keeps going. Even the curved vein grate, remember, what is that? It's the P50 times 100 at about what? Around 4%. Its efficiency goes down. And why do you think that is? Why do the grapes become more inefficient as the slope steepens?
Velocity increases so much it overtops.
Not that it overtops, but it splashes over. The momentum is forcing it to just go down the hill instead of falling in, right? Yeah. And then notice this one too. For grade A, the length is 4 feet and the width is 2 feet. And for grade 1A, the length and width are 2 feet. So length doesn't help you that much. They're pretty much acting the same. The length gives, I don't know, maybe a 5% change there, but it doesn't help you that much. So just lengthening your grade isn't going to help you. What do you think might help you? Yeah. You were talking about that yesterday, I think, or this morning. Can't remember. So lengthening your grade doesn't help because, as you saw on those efficient grades, most of the efficiency is coming when the water is going in near the upstream side of the grade. So if your grade isn't picking up all the flow, you might want to put two side by side as opposed to lengthwise. The length isn't going to help you. Put them side by side. Now sometimes they don't want to do that because this outside grate is in the travel lane and cars don't like to go over that. But if you're really pressed and you need to pick up all the flow, you can try that. So Anyway, it's just kind of an interesting one. So when we talk about inlet flow, weir flow at a grate inlet, we're not looking at the four sides. We don't look at the whole perimeter because this is a curve. So no water is coming in on this side. So when you're figuring out the perimeter or the length for your weir, you're only looking at the three sides. Okay? And this is the equation for weir flow and grate. And if you remember, weir flow equation is Q equals CW L H to the 1.5. So your P is your perimeter, and that's equal to your L, basically. It's an equivalent of that L, but we're only looking at three sides. And your weir coefficient will be 3, and that D is the flow depth in the gutter, right before it falls in. Okay? And then you can have orifice flow as well. Where would you have orifice flow?
When it's underwater, when it's submerged.
Why would it be submerged? It could be plugged up, but if it's plugged up, it's not really working, is it?
The flood, I guess.
If we have excess flow, and then we have bypass to another inlet, so that inlet could be designed as an orifice. And then
If you're on a slope, do you think you're going to have ponded water?
Be in a sag location.
Sag location. In a sag, you would have ponded water, like under an underpass or something like that. So if you're in on a slope, unless the slope stops pretty fast and you've got a flat area, you're not going to have ponding water. You probably won't have orifice flow. It's usually in the sag. And so the orifice equation is that C sub O, the orifice coefficient, is equal to 0.67. And you want the clear opening of the grate. And what that means is you can't just take width times length. You have to take out the area of the bars. So you want the clear opening of the grate. And that's multiplied by 2g acceleration of gravity times your flow depth, and you take the square root of that. So when you're finding your depth, that D, you want to take the average depth, because even if it's on a 2% slope, this edge will be higher than this edge. So you take the average of your depth. If you're in a composite slope, you also want to take the average of the depth. So weir flow occurs usually when the depth is less than 0.4 feet. And then orifice flow occurs when the flow is greater than 1.4 times the height of the curve. And then you have that transition area in between the two. So it'll start acting as a weir, and then it acts as an orifice and keeps going back and forth until you hit about 1.4 times the height of the curve. So this chart can help a lot. It's a little confusing, so I'm going to switch over to
I think it's input A.
right.
Yep.
So you have this in your binders as well. I know this is kind of tough to see. But, so to use this chart, it's going to help us figure out the grate capacity in the sump location. And so it's telling us in the bottom in this area, if you're in weir flow, it can help us find out what the discharge is. And up above, if you're in orifice flow, then this is where you use the top of it. Okay. What you'll notice here too is that it gives you these grates, and this P178 -4 is that P50 times 100. And and the one below it is the P50. So the times 100 is the bicycle safe one, and the other is not bicycle safe. And then the P1 1/8 is the P30. So a lot of times you'll see them written as that instead of the way they have them here. Okay. So what you need is your area, but you need the area without the bars. So you need the clear opening area. And what they've done here is give you the ratio of the opening area. So say you had a 2x2 grate, you would multiply that by 0.8. So it's 4 times 0.8, and you would get 3.2. And you can make your own line here, approximately 3.2, and just put it in. And if we're going to be using a 2x2 grate, remember on a Weir, we're looking at 3 sides. So what would the perimeter of a 2x2 grate be?
6 feet.
6 feet. So you might want to just come in here, and this is a transition area through here. So we don't have a line. But what you can do is just pick your own little line and bring it on up. Okay? You're probably going to have to do that in your workshop project, so I want you to know that. If your depth is above 0.4 feet, you're going to probably be in a transition area. If you have a perimeter of 4 feet, you might have Weir flow. It just kind of depends on what it is. You could be in a transition area though. So know that. What else? So yeah, that's really what I wanted to show you. Do you have any questions about this? Okay. And remember, this chart does not take into account the grade, so you would have to compensate for that. So I'll go back. And then the only other thing I want to bring up is this factor of safety. So your capacity of the inlet is divided by the design flow will give you your factor of safety. So if you're in an important area, if you're in a vertical sag or something like that, you might want to make your factor of safety a little higher, just so you're guaranteed, or you have more of a guarantee that the inlet will keep working for you, even in a serious situation. I think that's it for this, yeah. So we're going to do the workshop problems. It's 5 after 3. Do you want to take a break? You want to keep going? Who wants a break? No? Eric wants a break. Okay, so why don't you start on the workshop problems. There are a few of them. So I'll just read through the statement. We're going to analyze the grate inlet and sag first. Oh, before we do that, you want to see a video of that geyser coming out of the...
Sure. Yeah.
Is everybody on board? Sure. And look at the hole it's coming out of. It must be 4 feet wide. And it's a big hole with the manhole cover off. It's almost like a volcano, you know. It's really,
Yeah, the inlet is windows, got a
There comes the
Yeah, what would you do if you know, you came across that? I can help you.
Guys are going out scanning.
2:30 in the morning, you're just like, cartwheels. Like, I have places to be.
Yeah,
like, oh.
that's something. Okay. Enough
It's
time.
over. That's 2:30 on Monday morning.
Yeah, Eric, do you remember what happened, why they had that pressure?
I think I recall Jim saying that the water came in a rush. So there was, the peak discharge came in a rush, and it trapped a lot of air in the system and went under pressure, and the more water was pushed in there, and the air was jostling around, and it was shooting water out the top.
Yeah, next. Anyway, well, apparently when it first started, there was a car that was right next to it, and the manhole was flying off. That's what I remember Jim saying.